So, okay, go ahead.
Okay, thank you, Lamont, for the introduction. So my name is Jay Henderson, and I'm one of the researchers on this project. This was done as a collaboration between the University of Waterloo, the University of Lille, and INRIA, France. So vibrotactile feedback is very typical for touchscreens, and the reason for this is that we've kind of shifted devices with physical buttons like this Nokia phone here to devices with touchscreens that kind of have these virtual buttons. And virtual keys don't really have tangible feedback, so we use vibrotactile feedback to kind of combat that. So it gives the user confidence that they've actually pressed a button. So there's been research that's looked at tactile feedback for targeting, starting with Coburn mostly, who showed that multimodal feedback was effective for hitting small targets. Brewster and Hogan have also both looked at the effectiveness of tactile feedback for mobile interactions, and they've basically showed that they help users in accuracy. So specifically, our paper is looking at distal vibrotactile feedback. So we're motivated by situations where interaction location feedback might not be available. So for example, if you have multiple users using a display, it doesn't really make sense to vibrate the entire display. Or if the display is projected in air, it's kind of impractical to have vibration motors in the air. So in these cases, we wanted to explore whether or not there's a potential way to provide users with vibration feedback, particularly by an alternate location. So this idea of using another location for feedback is not new. McAdam and Maida looked at vibrating the wrist on the same hand that's interacting. And the premise of this is basically if the wrist is vibrating, the vibration will propagate to the hand, so you get kind of this virtual feedback while you're interacting. Tangana also looked at using vibration on the non-dominant hand's fingers to understand what's going on while using a pair of forceps with your dominant hand, particularly in computer-enhanced surgical procedures. So a lot of these systems in the literature, like McAdam, Maida, and Tangana, they all use specialized vibration systems. But what we're curious about is if you can support this dominant hand interaction with vibrotactile feedback from a commodity smartwatch on the non-dominant hand, or the non-dominant wrist. And we wanted to look at this for two reasons. First, there's an advantage to doing it this way. It's convenient, these devices are broadly available, and a lot of people understand what they're doing and their purpose. Second, a lot of vibrotactile feedback techniques have been explored on the wrist of the same hand that people are interacting with, which is actually not where these devices are typically worn. And we were also not aware of any previous literature that looks at this opposing location as a location for vibrotactile feedback. So that's the question we're asking in this paper. Can we use a convenience device like a smartwatch to provide distal vibrotactile feedback as a proxy for interaction location feedback? So in our study, we used two devices. We used a Huawei Nexus 6G smartphone where the user would interact and receive vibration feedback. And then for distal feedback, we used a Sony Smartwatch 3 where people would receive feedback upon acquiring a target on the mobile phone. Each device used an ERM vibration motor, which is basically just a standard vibration motor on commodity devices. And we used Bluetooth to facilitate communication between the smartphone and the smartwatch. So before we ran the main study, one of the big questions we wanted to ask is how do we actually provide this vibrotactile feedback? So do we provide vibration while the user's finger is within the entire target? Do we try and get the user to move closer to the center of the target and vibrate there in order to reduce errors by them lifting off? Do we tell the user that they've entered the target by just vibrating there at the edges, or do we not give them feedback at all? So we actually did a quick test using a Fitz's ISO task to compare this distal interaction to, distal feedback to interaction location feedback. And what we found is that essentially participants seem to prefer this fill style of feedback across both the watch and phone conditions. Participants also rated both the watch or distal feedback and phone or interaction location feedback quite highly, which showed promise for exploring this further. And one participant particularly noted that they felt it was amazing that we were able to rewire their brain to associate this distal feedback to an interaction location. So that gave some merit for studying this further. So after the pilot, we fleshed out an experimental design. So to reiterate, our goal is to assess how distal vibrotactile feedback or smartwatch feedback compares to interaction location vibrotactile feedback or under the finger feedback. And from the pilot, we determined that fill feedback was most appropriate. We also had some other design considerations, and these were that we wanted to look at smaller targets, and this is because of the literature. Vibration feedback is generally more beneficial for these smaller targets, so we figured that was a good point to look at. And also we wanted to look at the costs associated with Bluetooth delay for communicating feedback to the watch. So in other words, what is the cost of moving the feedback to a distal location, including the time costs of sending the message to start the vibration? And do the benefits outweigh this cost? So this led us to the following experimental design. So first of all, we have a series of target sizes that are inspired by typical target sizes on a mobile device. So 1 and 2 centimeters are fairly large mobile targets, and 1 centimeter is similar to the home button here at the bottom. 6.3 millimeters is actually drawn from Android guidelines, which is typically the smallest recommended button size. And then we have 3 smaller sizes. So 3.2 millimeters was about the size of a text key, 1.3 millimeters, which is approximately the inner-word spacing in a line of text, and 1.9 millimeters, which is approximately the height of a line of text before zooming. So this gave us 6 different target sizes that we were investigating. So the experimental task was a FITS ISO task. So basically participants were instructed to select the blue target as the starting point. They were to move their index finger from the blue target to the red target, and then lift their finger once it was within the red target. And this is when they received the vibrotactile feedback. Text feedback was also provided at the top left-hand corner, just to indicate whether or not the participant had completed the selection correctly. Alongside this, we have 4 conditions. So we have interaction location or phone feedback as condition 1. We have phone feedback plus delay, which was a Bluetooth delay that we calculated as 39 milliseconds as condition 2. We have distal or watch feedback as condition 3. And then no feedback as a control condition or condition 4. So in our evaluation, we have the following hypotheses. We hypothesize that vibrotactile feedback will improve targeting time compared to no feedback. As well, the user, this is largely due to the user having an additional indicator of acquiring a target, so we expect them to be faster. Second, we expect vibrotactile feedback to lower error rate compared to no feedback, again, because the user has this additional indicator of acquiring the target. Lastly, we expect participants to prefer feedback conditions over no feedback for the reasons I said prior, and we do expect people to prefer the phone feedback over watch feedback, largely because they're used to it. So this just kind of summarizes what we did. We had a within subjects design, 16 participants, and it was counterbalanced using a Latin square design. And basically we just collected over 23,000 targeting tasks to evaluate the phenomenon. So moving on to results of our study. Time was actually our most surprising result, since we thought that feedback would improve time, but we actually found the opposite. So the graph on the left here depicts average time to acquire a target on the y-axis by target width on the x-axis. So what we found was that no feedback, in gray on the graph, was actually faster than feedback, and in particular much faster for small targets. And that phone with delay and watch feedback were statistically significantly slower than no feedback. So no feedback gives a shorter time, but then as the targets get larger, they all kind of converge on the same time, seeing no benefit really either way. And we were really interested in investigating what might be going on here, so we looked at it a bit further. So we broke these results down into a Fitz's law analysis. These graphs are scatter plots of average time to select a target by Fitz IDs for each condition. We drew a line of best fit for targets greater than or equal to 3.2 millimeters, which are just typical target sizes on mobile devices. And I'm going to highlight two main components of this slide. So first, looking at targets from 2 centimeters to 3.2 millimeters, you kind of see all of these targets following a standard Fitz's law behavior in terms of time. And it doesn't really appear that feedback harms performance time in any of these typical targets. But then when you look at exceptionally small targets, such as 1.3 millimeters or 1.9 millimeters, you can see Fitz's law sort of break down. And you can see in the no feedback conditions, average time for these small targets lie exclusively below the line of best fit. But in the feedback conditions, average times lie exclusively above the line of best fit. And this is interesting because while we can't really measure what's going on in people's minds while they're interacting, we think that they might have felt like they actually could succeed when there was feedback there, but when there was no feedback, they kind of just gave up, which is why the time kind of just went off. We can see this as well a little bit in errors. The graph here depicts error rate by target width, and you'll notice that error rate drops as targets get larger. And we found that with feedback, people are more accurate, and particularly that in phone with delay and watch feedback, people are statistically significantly more accurate than no feedback. 1.3 millimeters and 1.9 millimeter targets are still very difficult to hit on a smartphone as they're much smaller than a finger. But you'll notice that people actually think they can hit them, and so oftentimes they do, which we see in this small little difference in error rate. And so we attribute this to people actually trying to hit the target. The last thing that we looked at was user preference. And the graph here depicts distribution of participants by preference rankings. And so we see that people value feedback, with no feedback being rated least preferred by 14 out of 16 of our participants. Also, one participant rated no feedback first, which you can see in the gray bar of the first bar. And they said they chose no feedback first because they were more frustrated when they got it wrong when there was feedback there. So essentially, if they were going to fail, they would rather fail with no feedback. So what's next for this research? So to sort of wrap up a little bit, as these interactive displays become more ubiquitous, such as virtual displays projected onto a surface or in air, we wonder if this vibration feedback, particularly when it's applied distally, will also assist in target acquisition, especially since these surfaces may be less familiar for interaction. Multi-user scenarios are also a clear use case for this phenomenon, so we think it makes sense to explore that next. Additionally, clearly we can imagine other places where you could provide distal vibrotactile feedback, such as your phone in your pocket, on smart glasses, on your headphones, or other wearables. But we figured that as smartwatches are one of the most popular wearables now, that their assessment was a good starting point. So we were also wondering if we could perhaps redesign vibrotactile feedback using the second type of feedback mentioned in our pilot study to kind of guide the user to the center of the target. This way, when they lift off, they're less likely to lift off outside of the target and more likely to actually acquire it. So to conclude, we present a Fitz's law analysis of distal vibrotactile feedback via a smartwatch. And thus, we conclude that distal vibrotactile feedback via a smartwatch can serve as an effective proxy for this interaction location feedback. And so I thank you all for attending my talk, and I can now take any questions.
So if you have any questions, please walk towards the mic and speak the mic. No questions? Okay, well, I have at least one question. So, well, even before I tell my question, please do not leave this session because I have one announcement to make. So, hang out a little bit. Okay, and Jay, my question to you is, so on this spectrum of like vibrations till no feedback at all, did you try to consider anything with let's say visual callouts or a little bit intermediary feedback level?
Yeah, so we definitely did consider using callouts. However, we kind of think that deploying a callout in this might introduce additional confounds because we just wanted to look at targeting. And then if we have another factor incorporated in that, it could introduce something different. However, we are curious kind of to see how these two things could be used in conjunction with one another and how this vibrotactile feedback accompanied with a callout could help users in acquiring their targets.
Thank you. One more round for Jim.